For today, we are going to continue on, we are going to look at the idea of melting. Yeah, we're going to look at the idea of melting. So, the idea of melting, I'm sure it's a familiar concept. To melt a crystal. All right, I'm sure you know what a crystal is. A solid substance, like a block of ice, is a crystal because it is composed of. I'm sure you saw that diagram in the first thing that you did. I don't know if it's in chemistry or for solid. A solid has compacted molecules like that, arranged in a ordered pattern, something like that, and and then it fills up the whole block. But for a gas or a liquid, it's usually they are spaced out like that, spaced out like that. But for a solid, they are compacted. There isn't much space between from one molecule to another. So that is what we call a crystal, something which is compacted and arranged in a regular pattern. So they are not disordered whereby one is there, another one is there. It's arranged in something, an ordered pattern. They are compacted in an ordered pattern. So to melt, meaning to dislocate this pattern, to disturb this pattern, that is what we mean by melting. So if we have a pattern which is, molecules are packed together like that, for us to disturb this arrangement, meaning we are going to melt, right? To disturb it so that these molecules can be free to randomly move about according to the thermal energy they have. So to melt the crystal, one must tear up the molecule, you must tear out the molecule out of the tight crystalline lattice, all right? And you have to cause it to be disordered, to break the bonds or the compact structure that is there. You must apply what? You must apply energy, all right? So this process, like we are saying, it requires energy, all right, which is usually supplied in form of heat. There, heat is the energy that is supplied. So I'm sure we are familiar with ice, that ice melts at 0 degrees, all right? Now this 0 degrees, if we just say ice melt at 0 degrees, we are not being comprehensive. We are not including other factors because pressure also comes to play a part, all right? So when we say ice melt at 0 degrees, we must say at standard temperature. Standard temperature, which is 76 millimeter of mercury, is the same as atmospheric pressure. At 1 atmosphere, if you leave ice under the influence of atmospheric pressure, you reduce the temperature to 0 degrees. This is the critical temperature where ice can either melt or solidify or crystallize, solidify. It can either melt or solidify. So when a crystalline material is heated, it begins to melt, all right? We know that under a certain temperature. That fact we know, all right? Now, what happens? So as we add heat slowly, all right, to that, if we add heat to that, containing those crystalline, if we add the heat, what will happen is, for example, ice, if it is at 0 degrees, you start adding heat slowly. Don't like put it on big chunk of firewood. Just let the stove, and then get a thermometer. You try this. Get ice and then put it on a stove in a pot. Then get a thermometer, put in the ice. What you see that the temperature will remain constant. All right? Temperature will remain constant until all the ice melts. So it will, if some other ice has melted, others are still not yet melting, temperature will remain constant. If you are at least using, you are introducing heat slowly, you have to make sure it is slowly. Don't put on the stove where it is like very hot. All right. So if you introduce heat slowly to a crystalline, what will happen is there will be a mixture of the solid and the liquid, but the temperature will remain constant until all the crystals have melted. So until all the crystals have melted, that is when we'll have temperature to change. So now, this type of phenomenon is attributed to the heat of fusion, all right? So that heat which you are adding slowly is absorbed as heat of fusion. It doesn't cause temperature change, but it is absorbed as heat of fusion. And this heat of fusion is the amount of heat energy which is required to do what? To melt a unit of mass of the crystalline material. If you melt it, if you apply that heat, which is called heat of fusion, it will cause the substance to melt, a solid or a crystalline material to melt. All right. And then we use the equation Q is equals to M multiplied by the heat of fusion. So if I'm applying heat to a solid, what will happen is it will keep its temperature until the whole solid has melted. After the whole solid melts, then the temperature will start changing. All right. Are we together?
Yes, sir.
Awesome. So it is the same thing. All right. We have talked about melting. All right. It melting and turning into, a liquid. But it is the same thing that applies to the other way around. It coming from liquid. All right. It is the same thing. If you are coming from liquid going to solid, the same phenomenon will take place. It's the same thing also when you are coming from solid to liquid. If you are coming from solid, from a crystalline to liquid, we are calling that melting. Going this direction from solid to liquid, we are calling that melting. All right. But coming from liquid to solid, we are calling that freezing. Freezing or crystallizing or solidifying. So we have all these terms. Freezing, if you hear the word freezing, it's coming from liquid to solid. If you hear the word crystallize, this word crystallize. Crystallize also means to turn from liquid to solid, because a crystal is a solid. And also to solidify, they are meaning the same thing. But from solid to liquid, we call it melting. If it is coming from solid to liquid, heat will be required. If it is coming from solid, all right, to liquid, you would need heat, all right? But if it is coming from liquid, all right, it's a liquid, like water is a liquid. If you freeze it to melt it, if you freeze it to make it a solid, from liquid to solid, heat is lost, all right? If you put water, which is a liquid in a fridge, the heat that the water has will be lost to the environment of the fridge. The fridge will get that heat and remove it from the liquid so that the liquid can solidify. So if we are coming from liquid to solid, the same equation will apply, but only that you may find the energy is negative. If you find the energy is negative, then you know that it was turning from liquid to solid. But if you find the energy positive, you find that it was turning from solid to liquid. Are we getting that concept? Negative and positive, are we getting?
Yes, sir.
What about the others?
Yes, sir.
Okay. Good to have you, Precious. Hello, Precious, are you there? Precious. Okay.
Yes.
Yeah, good to have you. I thought you were not going to join us today, this morning.
I'll be leaving soon.
Okay, but otherwise, how are you doing this morning?
I'm fine, and how are you?
I'm good. I'm good. Awesome. I hope you'll be able to catch up something where you have found us. We were just talking about melting, the idea of melting, and yeah. So we are saying that when something is melting, temperature doesn't change, but energy is absorbed in what is called heat of fusion. Heat of fusion is what absorbs the temperature. I mean, it's what absorbs the energy to convert it from liquid to solid, from liquid to solid, or from solid to liquid. All right. We are saying that from solid to liquid, we absorb energy. We absorb energy. We absorb, all right? We absorb that energy. But if it is coming from liquid, it's going to solid, then we give energy. We release energy. It's giving that. So in questions, the value of the heat of fusion will be given to you. So okay, this one of our friend has their mic on. So let us just continue on and look at just another phenomenon. Another phenomenon that which will just help you appreciate the idea of melting, or the idea of freezing and melting. All right, the idea of freezing and melting, what happens is that most substances, all right, when they are freezing or crystallizing or solidifying, they reduce the volume. All right, so if you find that if the liquid had a volume of this much, when it turns into a solid, its volume will decrease. That is the phenomenon. That is the behavior of most substances. When they are freezing, they usually reduce in the volume. All right, the density actually increases. Simbarasha, you have a question? Yes, I'm actually coming there to water. So I said most. So if you have, carbon dioxide or anything apart from water, water is the only, cantankerous character when it comes to this phenomenon, this idea. So with water, it's the other way around, all right? Most substances, when they're turning from liquid to solid, all right, the volume reduces. But with water, it is the other way around. It is the only known substance that behaves that way. I'm sure there could be other substances which behave that way, but I'm not very familiar with those. I know water. Water, if this was liquid, when it solidifies, it actually expands. No wonder if you are putting water in a fridge, in a container, don't fill it up with water. That container will burst, all right? For example, beer. Since in beer there is water. If you put beer in a fridge, all right, in a deep freezer, in that glass bottle of beer, you'll find that that bottle will burst. You find your beer is gone. Most of you ISDs, I know you don't drink beer, but that's just the scientific science behind that. Water, when it is cooled, when it solidifies, it expands. All right. So it is different from carbon dioxide, as we'll see on this curve. All right. So on this diagram, we are looking at just different states called phases. All right. When you hear the word phase, all right, when you hear the word phase, it's talking about something in terms of liquid, solid, and gas. All right. So this is a diagram just showing different phases. And on this diagram, we see that temperature is increasing in that direction. Here we have temperature, all right? And we have also pressure increasing in that direction. So what happens if you are at a very, very low pressure point, all right? If you are at a very, very low pressure point, you will require very small amount of heat, or the temperature will be very low to melt something. All right. So for example, anything like even a gas like carbon dioxide, or it's only again water that behaves in a strange way. With water, all right, when you increase the pressure here, if you increase the pressure, all right, meaning the temperature at which it will melt, or the temperature at which it will solidify, will increase. Temperature will increase. All right. Wait a minute. No, the temperature will reduce, because what it does is when you compact the molecules of water, all right, then they want to expand, but you want to compact them. So if you really want to freeze water by increasing a lot of pressure, you have to really reduce the temperature. But anyway, the main idea for me to show you this diagram is just to show you that this is a phase diagram that shows the solid phase, the liquid phase, and the vapor phase. So what happens is, if the temperature is very low and the pressure is very low, there's a thin line. A thin line, have you seen this line? This is the line that separates the solid. So this is the one that has frozen, the solid state, the frozen state, all right? So from the frozen state, as you continue to increase the temperature, what will happen is you will go into the liquid state, all right? So if you continue to increase the temperature and also the pressure, you will continue to go into the, from the solid state, you go into the liquid state. And if you continue again to increase the temperature, you will go into the vapor, or the gaseous state, all right? But then the gaseous state goes all the way down. Water can exist as a gas even at minus 15 degrees, right? As we are seeing. How can water exist as a gas even at minus 15 degrees if the pressure is reduced, all right? If the molecules of water are far apart, all right, what will happen to water is that it can still even appear as a gas, as a vapor, even at 15 degrees if you have reduced the pressure, right? But if you increase the pressure, all right, it can appear to be a gas like we normally know it at 100 degrees under the normal pressure that is when water appears to be a gas. But there's another interesting phenomenon that I would like just to explain right now, which is called sublimation. Have you guys ever heard of the word sublimation? This word there, sublimation. Have you ever?
Yes.
You have heard of the word sublimation, right?
Yes.
What is sublimation? Take it.
Changing of
This is when a substance changes its state from solid directly to gas.
Okay. So here now we don't just have to get the what's this definition as if it's abstract science. We need to get the practical and actual, the aspect, what really happens, what's the science behind. So what happens to the process of sublimation? As I've told you already, that this line here is a line that separates different phases. All right, it's showing us a curve separating a different phases. And there's this one is called the fusion curve. This other fusion curve is also separating the solid from the liquid. Now with sublimation, if you reduce the pressure, all right, have you seen? Pressure is going up in this way, but if you reduce pressure, all right, at a very, very low temperature, such as, minus 20 degrees or minus 15 degrees or minus 10 degrees, at that very, very low pressure, all right, it is possible for ice, if you maintain the pressure, for example, if you maintain the pressure at 2 millimeters of mercury, very, very low pressure, 2 millimeters of mercury. I don't know if you guys know how to convert millimeters of mercury to atmospheric pressure, but you can, because you know that 276, right? 276 millimeters of mercury is equals to 1 atmosphere. All right. So if we have, instead of 276, we just have something like a 2 millimeters of mercury. All right. Then the atmospheric pressure will be something like 0.0 something. I don't know. It will be very, very small. All right. It will be very, very small. So if we are way below atmospheric pressure at 2 millimeters of mercury, what will happen is, if we slightly just increase the temperature, maybe from minus 15 to minus 10 degrees, water, which is ice, you will find that you had a block of ice, but in an instant, it will all vanish like magic. You just discover you have a block of ice, but once you just increase the temperature, the ice has disappeared. You'll be like, where is my ice? Where is my ice? That is what happens when sublimation takes place. All right. And then it even reaches a point. Have you guys ever heard of the triple point of water? Triple point?
I haven't.
Anyone who has ever heard? Precious, have you ever heard of the triple point of water? Precious, are you still with us? Okay, so the triple point of water is the point at a certain pressure and temperature, all right? So pressure has to be there into consideration, and the temperature has to be there into consideration. And this triple point is here. It's about at 4 millimeters of mercury and at 0 degrees. In fact, it's even shown here. I'll show you. It happens not necessarily at 4, but at 0.01 degrees Celsius, and the atmospheric pressure will be 0.006 atmospheric pressure. At this point, all right, which is shown here on the curve here, triple point of water, all right, water can exist as both a solid and a liquid and as a gas at the same time. So you find that at this point, it's a very delicate point. You find that in a vessel like this, you can even find water as ice, water as liquid around it, and water as a gas there at a temperature of 0.01 degrees Celsius and at a pressure of 0.006 atmosphere. All right. But here it has been given as somewhere at about 4 millimeters of mercury. All right. So you should also know that you should read about how they use mercury to measure pressure, so that whenever we talk about millimeters of mercury, you should know what we mean, right? For the sake of science, you should get to know how they measure, because I read about it when I was in first year, so you guys should also read about it. So, but you should go home with this concept of triple point of water, that water in a certain vessel, in a certain container, can exist as both a solid, liquid, and a gas at about 0.01 degrees Celsius and at a pressure of 0.06 atmospheric pressure. Is that okay?
Yes, sir.
Okay. Okay. So alongside water, here we have water. Here we have carbon dioxide. This other diagram is showing just to give us an idea of something's carbon dioxide. We know carbon dioxide mostly as a gas because it appears to be a gas under room temperature. If we look at room temperature and pressure, we'll discover that carbon dioxide usually appears to be a gas. But carbon dioxide is not entirely a gas. It can also appear as a liquid. All right. It can also appear as a liquid, and it can also appear as a solid. We can actually have solid carbon dioxide. All right. Solid. We can have solid, we can have gas, liquid, and solid carbon dioxide. So what happens again is carbon dioxide freezes at a much lower temperature than water. So you have to know that. But with carbon dioxide, what happens is that when it freezes, its volume reduces. So volume reduces when it freezes, all right? And we have even seen the curve of the fusion curve. The fusion curve is the one that talks about turning either from solid to liquid or from liquid to solid, all right? It's like that. It's bent like that because it's actually a positive slope, because when pressure is being increased, all right, if you increase pressure, you will require a small amount, you require a little amount of temperature or heat to melt it. And if you just compress it too much, you will just, if it is like a solid, all right, if you compress it too much, all right, it can solidify even at a higher temperature, all right, even above its original melting point. If you just compress it too much, it can solidify. But with water, all right, at 0 degrees, for example, if you're at 0 degrees water, 0 degrees Celsius, if you increase the pressure, If you increase the pressure, what will happen is water will still be a liquid, because water wants to expand, but you are reducing you are increasing the pressure, trying to compress it. If you compress it, it will still remain to be a liquid, even at 0 degrees. No wonder its fusion curve is a negative slope. All right. Are we getting something there? Anything entering the head? Are we there?
Yes, sir.
Okay. But the most important thing that I would like you guys to go home with is the triple point of water. And the triple, just the phenomenon of triple point. Triple point, it means that a substance can exist both as a solid and as a liquid and as a gas under the same condition. You have the same condition, you have the same temperature, same pressure, and same environment. A substance can exist both as a liquid, as a solid, as a liquid, and as a gas. And that is what we call a triple point. So it may come in your quiz or in any multiple choice question. What is a triple point of water? Triple point, or what does it mean to be triple point? You will know that a substance can exist as a solid, as a liquid, and as a gas at the same time. And also, I'm sure now we have gotten to have just a scientific or a practical aspect of sublimation. I said sublimation, what happens is that a substance can turn from solid to gas, and this happens when you reduce the pressure. If you reduce the pressure, meaning the substance is free to move, all right? If you reduce the pressure, if, for example, if I reduce the pressure of water, even at a low temperature such as 5 degrees, negative 5 degrees, all right? At negative 5 degrees, I'm able to turn water from a solid to gas if I reduce the pressure, all right? But if I increase the pressure and continue increasing the temperature, I can only hope to change the state from liquid to gas like that. If I increase the pressure, then everything changes. But if I reduce the pressure, sublimation can take place. And if I also reduce the temperature. Are we okay on that?
Yes.
Okay. Okay. So we are going to end the first part of our lecture today here, but let's come back to the link so that we can just look at a few things under calorimetry. From there now, hopefully the next class will have to conclude the topic of calorimetry. After we conclude the topic, then you guys are warm and dry for exam. Is that okay?
Yes, sir.
Okay.